Hello everyone, welcome back to another Flan Talk. Today we're excited to have Awni Altabaa. He's done some very interesting work in generalization and reasoning for machine learning, and today he's going to give us some exciting new work on sample complexity and chain of thought. So thanks, Awni, and take it away.
Okay, great. Thank you. Today I want to tell you a bit about some recent work that we've done on um, trying to develop a theory of statistical learning for the CoT supervision setting, which has been very important in recent advancement in language models. So to motivate, maybe let's start with a question for ChatGPT. A seemingly simple question: which number is larger, 9.9 or 9.10? 9.10. So if you were to ask this to ChatGPT 5 instant and prompt it to give you the answer right away, it would use the wrong heuristic and give you the wrong answer, 9.10. But if you ask this to ChatGPT 5 thinking, it'll go through its own, internal chain of thought and then give you the correct answer, 9.9. Okay, so that's a bit puzzling. Let's try another question. So this is kind of a word problem style question. A forest has 1,000 trees. Each year's loggers cut down half of the trees remaining at the start of the year. In the same year, conservationists plant 100 new trees at the end of the year. After this process repeats for 2 years, how many trees are in the forest? So you can imagine this requires kind of a multi-step, uh, uh, reasoning process to solve. Again, we ask this to ChatGPT 5 instant, and it gives you kind of a made-up answer, a wrong answer. But if you ask this to ChatGPT 5 thinking, it goes through its internal chain of thought, it thinks for 23 seconds, and then it gives you the correct answer, which is 400. Okay. So one thing about ChatGPT is if you kind of click on this little thought for 23 seconds, it'll give you like a summary of the chain of thought it does internally, but they don't actually give you the real chain of thought. Models like DeepSeek would give you the real chain of thought that is going on internally, and this is an example of what it might look like. Um, so this would be something that looks like the training data that the model was trained on, so it knows how to do this. Okay, let's do one last example. So this is a problem of solving systems of linear equations. I made up three linear equations randomly, and then we're asking the model to solve for x, y, and z. Okay. Again, ask this to ChatGPT 5 instant, prompting it to give the answer immediately. It makes something up. These answers are not correct. But if you ask ChatGPT 5 thinking, it goes through its own internal reasoning process, and then gives you the correct answer at the end. Okay, so what's going on here? So ChatGPT Instant is attempting to produce the answer immediately in just one step. But to robustly compute answers to questions of this type, you need to do a multi-step reasoning process. So the basic idea is that CoT training provides a form of intermediate supervision to help the model learn the process of solving a problem, not just learn the answer. And so this is how ChatGPT thinking is trained, and it's carrying out the computation step by step, emulating some learned problem-solving procedure. And this enables it to arrive at the correct answer. Okay, so we are saying here that CoT supervision improves accuracy on reasoning tasks. And we might ask, how can we formalize and measure statistical advantage of this kind of CoT supervision? So this is what we're going to try to develop throughout this talk. We're going to try to come up with some learning theoretic framework that captures this statistical advantage. So some of the central questions that are motivating this work are, when does the CoT supervision reduce sample complexity compared to just observing end-to-end labels? How do we quantify the amount of added information in the CoT traces? And what are the upper bounds and lower bounds that govern CoT learning? Okay, so we attempt to answer these questions in this paper, which is going to appear at NeurIPS this year. And this is work done with collaborators Amar Muntasser at Yale and John Lafferty at Yale also. Okay, so this is the rough plan for the remainder of the talk. Uh, we'll first talk about how chain of thought is used in large training in large language models in practice. Then we'll try to formalize this as CoT supervised learning in a formal sense. We'll present some upper bounds, which make use of kind of the central quantity established in the work, which we call the CoT information. We'll talk about some information theoretic lower bounds and then close by presenting some simulations that test this theory to see whether it gives you kind of reasonable predictions. Okay, so uh, probably for this audience, you're vaguely aware of this, but to kind of give a backdrop for the talk. Um, Modern large language models can be broadly thought of as being built in three steps. The first is pre-training, then supervised fine-tuning, then post-training. In the pre-training step, or sometimes called the foundation modeling step, the goal is to just learn broad world knowledge and language ability. And this is done by next token prediction objective on large internet scale data. So at the end of this step, you have a language model. It can, predict what the next word is going to be in a given text, but it's not a helpful model yet. And then second step, the goal is to teach the model to follow instructions and perform tasks step by step. So this is how you get your, chat type model. So the data here is of a smaller scale, but typically much higher quality. Often it's involves human written demonstrations in Q&A format, and it includes chain of thought style rationales that the model is trained on. Okay, and then the final step, which includes a bunch of things, but is probably categorized under post-training. Here, the goal is to align the model outputs to human preferences, enforce safety policies, and enable some features like tool use and function calling. The data that's used here can vary, but it includes things like human preferences, which is used in RLHF or DPO. Um, then more data that you can do supervised fine-tuning on, for example, to learn how to do tool calling, as well as for certain kinds of tasks, you can generate synthetic data. Okay, so for us, our focus is going to be on the CoT supervision component that happens in the supervised fine-tuning step. And the main question that we're asking is, what statistical advantage does the CoT supervision provide? Okay, so first question is first, how are we actually obtaining these CoT traces to train on? And
Can
if
I ask,
you're a PhD, yeah.
can I ask a quick question there? Because you presented two versions of GPT. Can you reflect on what is different in the two versions with the three steps you just gave?
Yeah, so uh, you know, because it's OpenAI, we don't know the details of it. But
Hmm.
roughly for the purposes of this talk, what we want to think about is that uh, uh, JetGPT Instant is maybe trained less on chain of thought style data. In practice, it's still trained some on chain of thought data, and it can, if you prompt it correctly, generate chain of thought. So it's that kind of is a bit fuzzy.
Okay.
But ChatGPT thinking is trained much more on chain of thought data, and it's trained in a bit of a different way.
So it's not about it being executed in a different way, but really trained in a different way?
It's both.
It's
Uh,
both.
there's yeah, at inference time there's also a difference.
All right. Thank you.
Okay. Yeah, so again, our focus is going to be on the CoT supervision component. Okay. And then first question is, how are we obtaining the CoT data to train on? Uh, and if you're a PhD student, you might have received messages like this on LinkedIn, which are these like companies, different kinds of companies, whose work it is to get people, experts, or people that are trained in some other way, to write down or help create chain of thought data for these big models to work to be trained on. Um, and there's been kind of different trends on how this is done over time. More recently, there's been kind of a trend of replacing low-cost data labelers that are doing kind of more general purpose tasks with more high-paid experts like PhD students or something that are focused specifically on more complicated tasks like reasoning or maybe software engineering or things like that. Okay, so there's different methods to get these CoT traces. One method is that they can be human authored. So for example, written by domain experts or expert annotators, or they could also be mined from educational content that sometimes have step-by-step solutions. They can also be model generated. So one way to generate a chain of thought, if you already have some reasonable model to start with, is you can generate them by prompting and generate a large number, and then filter for only the best ones by methods like self-consistency or self-verification. And that gives you a more high quality, chain of thought data set that you can then train on. You can also do hybrid approaches where maybe the model generates them, but humans are in the loop and filtering, rating, or editing the chain of thought traces. And for certain kinds of tasks, it might be possible to also generate them programmatically. For us, we're not going to care so much about the specific way in which the CoT traces are obtained or what format they're in, whether they're in natural language or otherwise. We're going to develop an abstract model, and we just assume that the CoT dataset exists, and we ask what statistical advantage does training with chain of thought confer compared to traditional supervised learning from input-output examples alone. Okay, so let's try to formalize chain of thought supervision. There are two aspects to developing some kind of theory that says something about chain of thought. So one aspect is function approximation, so trying to characterize how the representational capacity of the model is expanded by allowing it to generate a chain of thought. And the second aspect is statistical, characterizing how much faster you can learn and how much more sample efficiently you can learn. So there's been quite a bit of work on this first aspect, on the function approximation aspect, and it's overall quite well understood. But the statistical aspect is less understood, and it's our focus for this work. So to kind of recap, in traditional supervised learning, the basic setup is that we want to learn some reference function, mapping from some input space and output space, and lying in some function class. And our learning algorithm observes labeled examples, X, Y pairs, where the input is random. And for now, considering the realizable setting, the label comes from this reference function. So the learning algorithm maps a set of such input-output pairs to a predictor. And the goal is to achieve small prediction error. So a basic intuition for how standard end-to-end learning works that will come in handy to develop intuition for CoT supervised learning. Let's consider the simplest possible setup where we just want to distinguish between two hypotheses. So the hypothesis class contains just two hypotheses. We can distinguish them once we observe some input where the output on the two hypotheses is different. So if the probability under the input distribution that we observe an input where the two hypotheses are different is epsilon, this will take roughly order 1 over epsilon samples. And then we can extend this to larger classes by union bounds or other arguments. And eventually this gives us a sample complexity that scales with the size of the class divided by epsilon, the target error that we're after. And for this talk and for this work, we'll see that we're mainly going to be interested in the denominator, in the epsilon dependence of the sample complexity, and we're going to interpret it as roughly the amount of information observed per sample. So we'll develop what this means more later in the talk, but one kind of initial intuition to have for why this can correspond to an amount of information is thinking to the agnostic setting where there could be noise and there's less information per sample. The rate is 1 over epsilon squared. And then if we develop different kinds of low noise conditions, we can interpolate between the 1 over epsilon and the 1 over epsilon squared rates. So we'll see that the CoT supervised setting, uh, the improvement in rate emerges in this denominator, and it captures the increased information per sample that CoT supervision provides. Okay, so before we get there, let's reflect a bit about the challenges of classical end-to-end learning for long-form reasoning problems. So what if we wanted to learn very complicated functions? And we want to do this more and more with modern machine learning. So in modern LLMs, we want to learn long-form multi-step reasoning, like mathematical reasoning or coding. And these problems are very statistically difficult to learn because these functions are very complicated and they're multi-step. Um, and if we observe input-output examples alone, this reveals relatively little information about the function per sample. So the basic idea of chain of thought supervision is just train with a stronger signal. So we're providing additional information to the learner, not only the input-output pairs, but we're also exposing the step-by-step computational trace of the underlying function that we'd like to learn. And so this reveals more information that's going to allow us to identify the function to be learned faster, or potentially much faster. So an intuition for why this is the case. Let's go back to this toy example where we just wanted to distinguish between two hypotheses. So now, rather than emitting just the final label as an observable output, in the CoT setting, we're emitting two observable outputs. One is still the final label, but the other is this chain of thought that we're going to denote as Z here abstractly. And this can be, you can think of it as like a sequence that represents the computational trace of the function. So now we can distinguish H1 and H2 if we observe X where either the output is different as before, or the chain of thought is different. So now it's much easier to distinguish the two hypotheses. And we can expect, if we define this I epsilon thing as the probability that either the output or the chain of thought are different, this thing is guaranteed to be more than the probability that the output is different. Now we need just 1 over this I of epsilon samples, whereas before this would we would need more samples to distinguish the two functions. Okay. So let's formalize a bit some of the details of the CoT supervised learning setting. So we're going to consider an abstract definition of CoT hypothesis classes as a family of functions mapping from an input space X to an output Y and a chain of thought Z. And then we'll introduce some notation to denote the end-to-end restriction of the function, so the component that's outputting just the final label, and the CoT restriction of the function, which is the component that outputs just the chain of thought. So for example, here in practice, the hypothesis class can be things like sequence models, like transformers, which output the CoT trace first, which is a sequence of some length, followed by the final output. Okay, and then a CoT learning algorithm is an algorithm that takes data sets of XYZ triplets and maps to a predictor, a function that predicts Y given X. And we can, say that some algorithm has given some sample complexity M epsilon delta. Here we're in a pack type setting. If whenever the sample size is bigger than M epsilon delta, we have that with probability at least 1 minus delta. The predictor returned by the algorithm has error less than epsilon in terms of predicting the final output. So the learning algorithm observes X, Y, and Z, the input, output, and the chain of thought. But the evaluation metric is just the end-to-end error. We just care about whether the final answer of the predictor is correct or not. Okay. So this is the setting. And our goal is to obtain statistical guarantees that characterize the advantage of training with chain of thought supervision. Okay. So the central challenge with this or at least one of the central challenges, is the asymmetry between the training objective and the testing objective. The training objective is the CoT empirical risk, but the test objective is the end-to-end error, just whether the final answer is correct or not. And this asymmetry prevents direct application of standard learning theory results. So one possible approach you could have to doing this, which is employed by recent related work, is to sidestep the symmetry by observing that the chain of thought risk is always smaller or equal than the end-to-end risk. Right. So here the approach is uh, instead of establishing guarantee on the end-to-end risk directly, establish a risk on the CoT risk, and that will then imply a guarantee for the end-to-end risk. So now the problem is symmetric because both the training and test objectives are just the CoT error, and we can apply standard learning theory results. So this kind of analysis would apply a sample complexity of order the BC dimension of the CoT loss class divided by epsilon to get a to get an algorithm, a predictor that has error less than epsilon. Okay. So the limitation of this analysis is that this is still giving us the same 1/epsilon rate that we had in standard end-to-end supervision. But intuitively, we know that observing the chain of thought should provide more information and therefore should enable faster statistical rates. So to capture this, we're going to need a more refined analysis that explicitly links the two different types of risks and quantifies the information content per observed CoT sample. So again, we're going to need to explicitly capture the amount of information that's encoded in the chain of thought that in terms of distinguishing hypotheses in the hypothesis class. So to do this, we introduce a new concept, which we call the chain of thought information. And this is kind of the central character in the paper. So let's kind of go through the definition a bit. So for a chain of thought hypothesis class and a distribution D over X, Y, and Z, so the input, output, and chain of thought, which we assume to be realizable by H for now. The chain of thought information is defined as a function of epsilon, the error, the target error, which is the infimum over hypotheses with error larger than epsilon of minus log the probability of the hypothesis agreeing with the ground truth, Y and Z, in terms of both the chain of thought and the end-to-end output. Okay, so this is just a maybe abstract equation, so I'll go through it one more time. So this delta E to E is a set. It's a set of all hypotheses with error more than epsilon. This is what makes the CoT information dependent on epsilon. It's a function of epsilon. And the CoT information has this kind of minus log thing that maybe reminds you of information theory, but it's defined as the infimum over these hypotheses with large error larger than epsilon, of minus the log probability of agreement. Okay. And we're going to see that the CoT information captures the statistical rate of CoT learning. So before to give you kind of a bit more intuition about this function.
Sorry, Ani, we had a comment in the chat about the last slide or question.
Mm-hmm.
Yeah, that's a minor thing in slide 42. Just to be
swapped?
sure.
Oh, they are swapped, yes.
Okay,
yes,
cool.
Yes.
Okay.
Yeah, sorry about that. Thanks.
Oh,
Okay.
Okay.
Yeah. So this should be ZY because this is HCT. Okay. Okay. So some properties of this function of the CoT information. As a function of epsilon, the CoT information is always bigger than or equal to epsilon. And the interpretation of this is that you always have more information when you observe the chain of thought. the chain of thought gives you more information than just the final label. It's a monotonically increasing function in epsilon, and it's monotonically decreasing in the hypothesis class. So when you have a bigger hypothesis class, you have a smaller CoT information. Okay. So the intuition here is when the CoT information is large, observing the chain of thought really reveals additional information about the target hypothesis, meaning in some sense that alternative hypotheses can't fake the reasoning steps in the target's chain of thought, so you can distinguish them. And this then ultimately implies that observing a chain of thought sample is more valuable than an end-to-end sample. Okay, so this is kind of the simplest version of the type of result that appears in the paper, and this is kind of gives the main story. So let's consider the finite hypothesis class case for now, for simplicity, and we're still in the realizable setting. The learning rule that we're considering is the most natural one, the CoT consistency rule. So given a sample S, just take all hypotheses that are consistent with S in terms of both the output and the chain of thought. So you're restricting to hypotheses that agree with the sample for all data points in terms of the output and the chain of thought. They match exactly. So this learning rule has an end-to-end error sample complexity that where the numerator is just the thing that you would expect that you see in the standard setting. It's depends on the size of the class, log cardinality of the class, plus some confidence term. But the interesting thing is in the denominator, now what you have is rather than epsilon, you have the CoT information. And remember, the CoT information is always larger than epsilon, and it can be much larger than epsilon. And so this sample complexity is more favorable than in the standard end-to-end supervision setting. So again, the meaning of a sample complexity here is if your number of samples is more than m epsilon delta, then with high probability, your learning rule returns a predictor where the end-to-end error is smaller than epsilon. So again, the error that we're interested in is just the error on the label, on the final output. Okay. So the takeaway here is that we improved the standard, the usual 1 over epsilon rate to a potentially much faster 1 over CoT information rate. And we can interpret the ratio of CoT information to epsilon, this function, as answering the question, how many end-to-end samples is a single CoT sample worth? Okay, so if this is large, then the CoT information is very valuable because it's worth many samples, many end-to-end samples. Okay, and we can think of this geometrically. So in this figure, along the x-axis, going to the right, are increasing sample size. And what we're drawing in each panel is some representation of the end-to-end consistency sets, which is in red, and the CoT consistency set, which is in blue. So the CoT consistency set is always smaller intuitively because you have more information. Yeah, there's more. You can narrow down your set more, and as you go to the right, you're shrinking faster. So this is kind of one way to interpret the faster learning rate is that your consistency set is shrinking faster as you increase sample size. And the rate at which it's shrinking is characterized by the CoT information. Okay. So I think that gives the main intuition. But of course, in practice, we're interested in infinite classes rather than finite classes. So we can extend the result to infinite classes, where the dependence on the size of the class can now be replaced by a VC dimension of the CoT loss class. But again, the important thing is that the epsilon dependence in the denominator is again the CoT information, which is what ultimately gives you the faster rate. Okay. So far we've been talking about the realizable setting, where the distribution D over X, Y, Z triplets is realizable by H. And then from here, you might ask, what if D is not realizable by H? And I'll give a quick preview of what happens here. So in general, in the agnostic setting, CoT supervision can be detrimental, unlike in the realizable setting where you at least have sample complexity at least as good, potentially much better. In the agnostic setting, there is a sense in which CoT supervision can actually be detrimental in kind of pathological settings. And I'll give you one example where this can happen. So suppose your distribution D over X, Y, and Z are such that the output component is realizable by H, but the CoT component is not realizable by H. And in particular, consider the extreme example where D is such that the minimum end-to-end error achievable by your hypothesis class is exactly 0, but the minimum CoT error achievable by hypothesis class is just 1. You can't capture anything about the CoT behavior. So in this case, if you were to apply CoT ERM, CoT empirical risk minimization, you get no guarantees because the CoT ERM learning rule just restricts to the full class. You always just get the full class because you can't capture anything about the chain of thought. And so you have no guarantees. But of course, because the minimum end-to-end risk is 0, you're actually in the realizable setting in terms of end-to-end learning, and you can get a 1 over epsilon times VC rate if you just throw away the CoT samples and just train on the end-to-end samples. So this is kind of an extreme example, but it conveys kind of what makes this a bit more complicated. So in order to extend our results to the agnostic setting, we need a different variant of the information that instead links the excess CoT risk with the excess end-to-end risk. And so this variant can be interpreted as a measure of how aligned the observed CoT in the data distribution is with the hypothesis class. If the hypothesis class captures the CoT well and captures it in such a way that learning the CoT components of the distribution well implies better end-to-end performance, then you get faster rates. So this has been just a preview, but if you're interested, please see the paper for more on this. And next, maybe let's talk about some lower bounds. So far we've established some statistical upper bounds, which are results of the form, let's say CoT supervision enables us to learn at least this fast. And the answer is expressed in terms of the CoT information. But if we really want to determine if the CoT information is fundamentally the correct characterization of the statistical rates for the setting, we also need corresponding lower bounds. So results that says learning with CoT supervision will always require at least this many samples. Okay, so here's one lower bound of this flavor. Fix the distribution D over inputs and let x1 through xm be sampled IID from this distribution. And the result says for any H star, for any reference hypothesis in your class, if the sample size is smaller than log 1 over delta over CoT information, then with probability at least delta, there exists some hypothesis H that has end-to-end error, at least epsilon, which is indistinguishable from H star on a sample. And then moreover, you can show that for any algorithm, for any learning algorithm, the worst case expected risk is at least this expression that's supremum over hypotheses and epsilon levels of this expression in terms of the CoT information, uh, uh, I of epsilon. And the basic idea for this result is it's a two-point method. The idea is to reduce to binary hypothesis testing. So this method is due to LeCam. So the message here is that we're getting the correct 1 over CoT information type lower bound dependence. So it's this lower bound is giving us the expected scaling with respect to the error parameter, and the CoT information appears, but it doesn't scale with the size of the hypothesis. And this is a limitation of two-point methods. We didn't make any assumptions on the size of the hypothesis. We didn't try to capture that in the lower bound. So the next result is going to be a lower bound that scales with the size of the hypothesis, and we're going to use Fana's method from information theory for it. So this is the result. Let me just describe it at a high level. So again, similar to before, we're fixing a distribution over inputs, and we have a sample of m inputs. The result says that if for any algorithm, if the sample size is small in the sense that it's smaller than in the numerator, this log m captures the size of the class. It's a covering number or a packing number with respect to a metric that depends on end-to-end disagreement. And in the denominator, we have the CoT information appearing. And in particular, it's this relative CoT information between a pair of hypotheses, and we're taking an average over pairwise CoT information. And then there's a supremum over priors. So this is maybe a bit abstract to get just over a slide, but the main message here is that this expression scales with the size in the numerator, scales with the size of the hypothesis, and depends on the CoT information in the denominator, which is what our statistical upper bounds look like. So if the sample size m is small in this sense, then the end-to-end error must be large for at least some reference hypothesis H star for any algorithm, in the sense that if you take the supremum over H star, then the probability of end-to-end error more than epsilon over 2 is at least 1/2. Okay, so if the sample size is smaller than this expression that scales with the size and depends on the CoT information, then you must have error at least order epsilon. And then the idea for this result is to construct a packing of H with respect to an end-to-end metric, and then use Fana's inequality from information theory and relate the mutual information to the CoT information. Okay. And then the main takeaway from these lower bounds is that they validate the CoT information as being, in some sense, a fundamental measure of the statistical complexity of learning under a CoT supervision. Okay, so to close out, I want to explore some simulation results that try to test for the predictions of this CoT information theory. So we want to ask, how well does this theory capture the statistical advantage of training with CoT supervision in practice? Okay, so we're going to have this basic experimental setup. For each experiment, we'll consider some CoT hypothesis class, and we'll fix a distribution D over inputs and fix some reference hypothesis H star. And then we're going to exactly compute the CoT information for this distribution in this hypothesis class. This will be possible because we're just going to consider finite hypothesis classes for these experiments. So we compute the CoT information exactly. And then we run simulations to evaluate the statistical rates of learning with end-to-end consistency, which the end-to-end consistency rule, which corresponds to end-to-end supervision, compared to the CoT consistency rule, which corresponds to CoT supervision. And then the question here is, does the CoT information accurately capture the statistical advantage? Does it give accurate predictions about the uh, advantage in sample complexity that's observed empirically? Okay, so um, let's consider one example here. So in practice, the way CoT supervision is implemented is by using a sequence model class, like for example, transformers, um, and training the model to generate the chain of thought as a sequence, token by token, before returning the final output. So here our goal is to consider like a toy setting that captures um, some aspect of this autoregressive generation. So what we're going to do is we're going to generate tokens autoregressively for t steps by a linear function that depends on a fixed size input of the history. Okay, so uh, this is kind of a formalization of what that means. The input space X is going to be variable length sequences in some alphabet sigma. The chain of thought is going to be sequences of length t. And the final output is going to be just a single token in that alphabet. For now, let's just consider the binary alphabet. And we're going to use a linear function to generate the next token. So it's going to observe a window of size d, and it maps a sequence x uh, of some arbitrary size to a sequence of that size plus 1. And the way it's doing it, the additional token that it's adding is we're just applying a threshold to a linear function applied to the window of the past D tokens uh, in the sequence, in the input sequence. Okay, and then we generate a hypothesis class. The way we do it is for each hypothesis in the class, the CoT output is a sequence of T tokens, where it's just the tokens generated by this autoregressive function step by step. And the end-to-end output is just the last token that it's generating. And for the experiments, we'll take the window size to be 8, the number of iterations to be 16, and the weight class is weights for the for this window of size D, taking values -1, 0, and +1. Okay. So this plot here is showing on the x-axis. So each point is a pair of hypotheses in the class. On the x-axis is the end-to-end disagreement between the hypotheses, the probability of end-to-end disagreement. On the y-axis is the relative CoT information between two hypotheses. So this is capturing how well these two hypotheses can be distinguished from a random sample. And the message here is that the relative CoT information is always larger than the end-to-end disagreement, which is interpreted as giving us more discriminative power to distinguish between hypotheses. Okay, and then we can compute the CoT information function itself directly as a function of epsilon. So along the x-axis is epsilon, going from epsilon equals 1 on the left to epsilon 10 to the -2, getting smaller on the right. And the y-axis is the CoT information. The dashed line is the line y equals epsilon, and the vertical dashed line is this critical epsilon, which is the minimum non-zero end-to-end error among hypotheses in the class. Okay, and then the message here is that the CoT information as a function of epsilon is always larger than epsilon, and this is interpreted as uh, uh, CoT observations giving us more information, allowing us to learn faster. Okay, and then from here we'll just run simulations that measure the empirical sample complexity. So on the left side is empirical sample complexity. So along the x-axis is target error level epsilon. On the y-axis is number of samples. And then we have two lines. The green line is the CoT consistency rule. The green line is the end-to-end consistency rule. So end-to-end consistency always requires more samples to achieve a given error level. Okay. And then on the right side, we're plotting the probability of getting a predictor that has exactly zero error as a function of sample size. Okay, so the CoT consistency rule returns a predictor with uh, with zero error much faster in terms of sample size than the end-to-end consistency rule. We see a roughly one order of magnitude difference here. Okay, so the takeaway here is if you take this CoT information that we computed, divided by epsilon, and take the limit going to zero, this gives us roughly 6, which suggests a 6 times gain in sample efficiency if you want to learn the function exactly. And this agrees with what we observe in practice pretty well. So the empirical sample complexity that we have indicates a roughly 5 times advantage for CoT supervision. So the way to see this is here. On the left side, the sample complexity goes to roughly 20 for CoT consistency, but it's roughly 100 for end-to-end consistency, so roughly a 5 times difference. And a different perspective on the right-hand side, which is more probabilistic, implies something like a one order of magnitude, so maybe 10 times. So it's what we observe is so the theory predicts somewhere in the middle of these two numbers, and they're relatively close. Okay, so that's one example. Another example is learning regular languages. So L is some regular language. The end-to-end function is just membership of a string in the language. So one if the string is a member, zero otherwise. And the chain of thought sequence here, we're taking it to be the sequence of states, the state trajectory for a DFA that recognizes the language. Okay, so it's the sequence Z1 through Zn, where these Z's are the states of the DFA that recognize the language. Okay, and for H star, we'll consider this DFA. And this plot here is showing the CoT information to epsilon ratio as a function of epsilon. Okay, so on the y-axis is CoT information divided by epsilon. On the x-axis is epsilon. Epsilon is getting smaller as you go to the right. And we see, and then the different lines here in different color are us varying the level of CoT detail. And the way that we vary the level of CoT detail is we just control how much of the state trajectory is observed. So for the line 10, this is observing the full trajectory. For 5, it's observing half the trajectory and so on. And we see if you're observing the full trajectory, this limit goes to roughly 600 as epsilon goes to 0. Okay, and we can do the same thing. We can empirically evaluate sample complexity for learning this regular language. On the left-hand side is the same plot as the empirical sample complexity, the number of samples you need to get a certain error for CoT consistency versus end-to-end consistency. And on the right-hand side is the more probabilistic measure of this, which is as you vary sample size, what's the probability that your learning rule returns a predictor that has exactly zero error? Yeah, so again, we see that the CoT consistency learns with much fewer samples and much faster. And looking at the actual numbers, so if you take the CoT information that we compute, take that ratio with epsilon, and take the limit as epsilon goes to 0, this converges to about 600, which would predict a 600 times gain in sample efficiency. And the empirical sample complexity gains that we have are, again, in that same order of magnitude, kind of sandwiching the prediction. It's between 100 and 1,000 times for CoT compared to end-to-end. And this we see from the figures in the previous slide. Okay. One extension to this, so far we've been looking at very simple, hypothesis classes that are finite, where we can exactly compute the CoT information. in practice, we're going to be interested in finite, maybe parametric, maybe neural network classes. And we don't have access to the data distribution, of course. So one question is, can we estimate the COT information from data? And informally, the answer is yes. So it's possible to estimate the COT information consistently from random samples uniformly in epsilon. So the COT information is a function of epsilon. We can have an estimator that is close to the COT information for all values of epsilon. And the implication here is that we can estimate the COT information for complex classes if we have enough data by setting up an appropriate optimization problem on these random samples. The optimization problem comes from this infimum form of the COT information. And this would provide us with a means of quantifying the value of CoT supervision for different kinds of model classes and different tasks. And this could be perhaps useful in comparing different methods of generating CoT traces to train on, and maybe helps us select among them as we scale up. Okay. So maybe let's conclude and open it up for some discussion. So the key message here is that we developed an extension of standard statistical learning theory to capture the CoT supervised setting with some implications about modern language models and the way that they're trained. We developed an information theoretic characterization of the statistical advantage of CoT supervision. And I think there are many really interesting open questions and directions for future work here. Maybe I'll mention a few. One is to explore the role of chain of thought in out-of-distribution generalization. So we observe empirically that chain of thought training can improve out-of-distribution generalization. And this is, I think, pretty intuitive. With chain of thought supervision, you're pressuring the model more to learn some given algorithm. And if you learn an algorithm correctly, then you can generalize, as opposed to you just learn some pattern matching to just predict an output. Another aspect is the use of reinforcement learning to learn chain of thought reasoning. So far, this theory is considering the use of chain of thought in the SFT step of building large language models. More recently, RL has been playing more and more of a role. So that would be interesting to explore theoretically. There are aspects of scaling that are interesting. How a chain of thought scales. Is it the same or different than in the pre-training stage? And then another, I think, interesting aspect that maybe the chain of thought measure can have something interesting to say about is how to design an optimal representation for chain of thought. So far, large language models really will just use natural language to represent the chain of thought because that's what they're trained on. Humans can only produce chains of thought in natural language, and that's what they're trained on. But I think it's easy to imagine that for machines, the optimal representation might be quite different, and there might be representations that are more efficient, more robust, and that enable faster learning. So I think it would be interesting to try to explore how to search for such representations, and perhaps the CoT information measure can be helpful there. Okay, so I think that's all. Again, I want to say, shout out to my collaborators, Amar Montasser and John Lafferty. And yeah, maybe we can have some discussion.